And welcome Calculus 3 students. We are expanding our definition of divergence to 3 dimensions. We will be taking our gradient, or our divergence of f, as the dot product of the gradient of that vector field f, and we'll just take the partial with respect to x, y, and z in order to get that divergence of the vector field. Now note that if the divergence of our vector field f is equal to 0, then our vector field is source free. So let's find our divergence of f. So all I'm going to do is do the dot product of this x, y, and z, which means I'll just take the partial of each one. So the partial of x with respect to x is 1, the partial of y with respect to y is 1, the partial of z with respect to z is 1, and therefore I get that this is 3. This means that the divergence is positive and the flow expands outward in all directions. Pretty cool. Here's the divergence for our B question. I'm going to do the same thing. I'm going to take the partial with respect to x, so that would be 0 for our first one. The partial with respect to y is again 0, and the partial with respect to z here is again 0. That means that our divergence of this vector field is 0, which also means that this vector field is source free. For C, same thing again. Do the dot product here, which means I just take the partial of each one. Partial of the first one with respect to x is 0. Partial of the next one with respect to y is 0. The partial of z with respect to z is 1. This equals 1. What this means is that x and y don't contribute at all to the divergence, but the z component produces a non-zero divergence, which means that it expands out in a spiral flow as noted here. For our next example, we are going to use theorem 15.8. Notice they want me to compute the divergence of the radial vector field, and if I just rewrite this as this x, y, z over x squared plus y squared plus z squared to the 1/2 power, you can note that in this case p equals 1. So I will say that the divergence of this vector field then can be simplified to 3 minus 1 over absolute value of my r to the first power. So this is just going to be 2 over this vector. Alright. In example 3, they're wanting us to get an intuitive sense of what's going on about the divergence, and we're given this circle of radius 2 centered at the origin, and they want us to determine the two-dimensional divergence at the point 1, 1. So here I am at the point 1, 1. What is the they want me to say whether or not the divergence is positive or negative. Well, at this point I can see that my f and my g functions are both going to be increasing. So that must mean that at that point the two-dimensional divergence is positive. For B, I'm just supposed to compute it, so let's just go ahead and compute this divergence of this vector field. F, I'm going to take the partial of x squared with respect to x, that's going to be 2x. Partial of the y with respect to y, that's going to be a 1. And then I'm to compute this at the point, so at the point 1, 1, meaning x is 1, y is 1, so if there were x's and y's in this, I would plug that in. I would get that this divergence of this vector field would be 2 times 1 plus 1, so that would be 3, which confirms the fact that it is positive. In this C part, we are determining what regions the divergence is positive or negative. Oh, we don't have to look any further than just noting where is this going to be greater than 0. Solving for this, I will get that x greater than negative 1/2, my divergence, notice here's where x is negative 1/2, and you will note that my divergence is positive in this realm, and anything on the other side of this, my divergence is negative. So it's where it's either expanding and how it's changing. So on the D part, we are to look at where we have our tangent line, and if you'll see, those tangent lines occur right about here and here, which would be at the x equal -1 point, and at this point we note that the flow is out of the circle, and that means we have an outward flux across C, and that would be positive. In our next example, we're going to compute the curl of our vector field. So I'm just going to follow here from our cross product, A cross R, and let's just substitute in for what we have for our A1, A2, A3. So here we have, and this is going to be A1 is going to be, in our case, A1 is 1, and then we have -1, 1, and our R in this case is our X, Y, and Z. Computing that cross product and getting the determinant, you will end up with our result as being our A2, which is -1 times Z minus A3 is 1 times the Y, and I'm just going to go through and compute for the rest of these. A3 is 1 times X minus A1 is 1 times Z. That one was a little nicer. And then next one, A1 is right here, that's 1 times Y, so that's Y. And then minus A2 is -1, and then times my X, oops, that's supposed to be plus, and this K component, and simplifying that is going to look like minus Z minus Y. I'll just write that down. So we now have our vector field F. We need to do the curl of F, so I'm going to say I would like the curl of F, which means I'm going to be looking at this I, J, and K component, and I will then write in the partial of each, and in the denominator here I'm going to have my F, which is, the denominator in the lower, I'll just go ahead and write these in, these partials, and then we'll substitute those in. Alright, so here's my cross product. In computing that, this is what I'll get. In other words, you can note that you could take out factor out the 2, and you will notice that it is the -1, +1, -1, +1, which means this is just the vector 2A. Now, if I would like to know what the magnitude of that curl is, I can say that the curl of F is basically this, and if I want to know the magnitude of that, I'm just going to find the magnitude of this thing right here, and it's going to be 2 times square root of 1 squared plus -1 quantity squared plus 1 squared. So the magnitude of this is going to be 2 square roots of 3. If you'll notice, this section has been all about, and this whole chapter has been about defining things and then doing their computations for each. In order to find the gradient field for F, we are first going to have to find the partials of each one of these with respect to X and Y and Z, just going all the way through here. So the partial of this with respect to X, leaving everything the same, I'm going to have -1/2. This is going to then end up being leave the inside alone, x squared plus y squared plus z squared, all to the minus 3/2 power. Take the derivative of the inside with respect to x, that's just going to be a 2x. And simplifying this, we're going to end up getting this negative x over this x squared plus y squared plus z squared to the 3/2 power. And if you'll notice, I could just say that this thing is then equal to negative x over r cubed, because r happens to be this deal right here. So I could say that, and I'm going to do the same calculation for the partial with respect to y and then z, so it's all going to look the same. So in other words, when I get finished with this, my vector field F is then going to be just that gradient of 1 over the magnitude of r, which is how it's listed in my definition, and this is just going to be minus the x, y, and z of my magnitude cubed, because they're all the same. So it is just my vector r over that magnitude cubed. So in finding my potential function, you can see that that potential function then is this right here. So we could say that is from that potential function, the 1 over the magnitude of r. Alright, in applying 1511 for B, we're going to find this dot product. What we're going to need to do is find the gradient. My dot product of F is just going to be this gradient, and just writing down what I calculated my F to be as magnitude of r cubed. Simplifying this just a little bit and writing it down. Alright, I get this just from this theorem 1511 here. Now we can do a similar thing to what we did here in A, and we will find that this right here is going to be equal to, so let me just fill this in, minus this r. This right here is going to be equal to negative 3r over magnitude of r to the 5th. And this part right here is just going to be equal to 3. So I'm going to have 1 over, and simplifying this, if you go through the algebra of this, you will see that this equals 0, which would then be consistent with theorem 15.8 when p is 3, which is what we have. You'll notice here p is 3. Next we have a summary of the properties of our conservative vector fields, and I include this just so that you'll have that in your notes whenever you go to take your exam. Alright, if you have any questions, be sure to email me.